Hello Varun, good evening. Hello, are you ready? Hello, Varun, are you there? Yeah, okay. So, we got all the results of your quarterly exam, first terminal exams. Yeah? Yes, any problem? Are you able to hear? What happened? Tell me. Yeah, I think so. Okay then. Okay. Hope you have enjoyed your holidays also. Tell me about your performance, results in the first terminal exam. I am able to hear, man. Okay. There is some time delay, it seems. I think your broadband speed is very low. Traffic is very high. That is why it takes more time for you to reach me. Okay. Doesn't matter. We'll start with the next lesson. The next lesson is light reflection and refraction. That is the lesson we are going to learn from today onwards. Okay. Right. Light reflection and refraction, which is the very interesting topic also, which we find playing a vital role in our daily life. You can learn, after learning you can apply in your daily life, or we can learn from the daily life. In such both the way, it is very much interesting. Okay. Here, there are so many phenomena. Among this, we are going to learn only two, reflection and refraction. Reflection and refraction. Only two phenomena we are going to learn in detail. Right. Here, we are able to see a variety of objects in the world around us, because we are endowed with the greatest gift by the God, eyes. You know, eyes are the very precious gift, which is a boon for us given by God. Using this, we are able to see a variety of objects. But, however, we are unable to see anything. Though we have got eyes, we are not able to see anything in the dark room when there is no light. Only on lighting up, the room becomes bright and things become visible. That means without light, our eyes cannot see anything. No object is visible without light. In such a way, light is playing a vital role. Now, there may be a question which is raising in your mind. What makes things visible? What makes things visible? Now, during the day, because of sunlight, the sunlight is prevailing everywhere, and that helps us to see objects. Because an object reflects most of the light that falls on it. I say that it is not totally reflecting. I say most of the light which is falling on it. It means that maybe some part of the light may be absorbed, some part may be reflected, or some object may totally reflect, or some object may totally observe. So I say that part of the light is, most of the part of the light is which is reflected when the light falls on it. Yeah, let us see one by one. And this reflected light, when received by our eyes, is only enabling us to see the objects. So though the lights are falling on the objects, the light after falling on the object should reach our eyes, right? Then only we will be able to see the things, so that the things becomes visible. Why I am saying this? Because there may be some object, the light may be falling on that, and you are standing somewhere else. You cannot see the object because the light which is falling on those objects should reach your eye. That is within the vicinity, we say. Then only you will be able to see the objects. Right. Here, just now we asked, there are so many phenomena. What are the other phenomena which is related to light? You asked me, isn't it? So here you can see there are different phenomena. You can see that this is the diffraction, we say. Diffraction of light, reflection of light, refraction of light, interference. Like this, there are so many phenomena associated with the light. If you go to higher classes, you will be studying in detail about the other phenomena, like 11th standard and 12th standard, we will be talking about the other phenomena. So since it is a basis which is forming in the 10th standard, we are going to learn only about reflection and refraction. And here, when you are talking about this reflection and refraction, it is making use of the straight line propagation of light. What is meant by straight line propagation? Propagation means proceeding forward, moving forward. That is called propagation. So straight line propagation of light means we understand that light travels in a straight line. So that property is only made use of to study about these two phenomena, reflection and refraction. Right. Now, by observing the common optical phenomena around us, as we see in the day-to-day life around us, we may come to the conclusion that light is always traveling in a straight line. Because always, right from the lower classes we have been studying, light travels in a straight line. Right. The fact is that the source of light is casting a sharp shadow of an opaque object, points to this straight line path of light, usually indicates that a straight line. That is, in the path of light, when you are keeping an object, opaque object, what will happen? It is hiding the light, so that behind that object, opaque object, a shadow is formed. So it is because we assume that the light is traveling in a straight line. When it is traveling in a straight line, when obstruction is there, it will cast shadow. Otherwise, in the other way, if shadow is cast, it means that the light, the straight line path of the light is obstructed. So that we understand that, indicate that this phenomenon indicates that the light is traveling in a straight line. Isn't it? So that is what we are going to use this phenomenon in this. But on the contrary to this fact, if an opaque object on the path of light becomes very, very small, like you take an example of sun. Sun is giving out light, right? In between, the moon is coming, right? If the moon comes, when you compare the distance of the sun and the moon, it is very, very large when compared to the size of the moon, isn't it? So in this way, similarly, here also you can see, I am keeping a small solid disk, right? That means a small one, object is small one, right? And when this object is very small, it seems that light has a tendency to bend around it and not walk in a straight line. This is what I said. You can see here, the moon is hiding the sun, right? Though it is an opaque object, the sun should be hidden completely. But you can see that there is like a diamond ring, gold ring, you can see that there is a light which is visible. Why? Because when this object, when compared to the distance between sun and the moon is larger when compared to the size of the moon, the sunlight is bending on the edges around the moon, so that the light is visible around the moon. we are able to see the light very clearly. So this property what we call as diffraction of light. Diffraction. Sometimes some people say diffraction. Okay, it is only a word, but actually it should be pronounced as diffraction of light. Right. So now we understand that light is not traveling in a straight line. It is able to bend also, bend around the edges. We simply put in a nutshell, the bending of light around the edges is called the diffraction of light. Right. Now then the straight line treatment of optics is failing. We can't say that light is always traveling in straight line. Sometimes it is bending like this. So to explain this phenomenon such as diffraction of light, scientists assume that since it is bending, light may be considered as a wave. Right? So now they say that light is behaving like a wave. It is not only traveling in a straight line, but it is behaving like a wave. Right? Now this wave theory you are going to study in higher classes, 12th standard, wave theory of light. Now earlier we thought that the straight line propagation of light. Now people have understood that light is not traveling in straight line, it is traveling like a wave. It is wave in nature. Again there was a problem. In the beginning of 20th century, it became known for the wave theory of light often becomes inadequate. It is not sufficient to explain when it comes with the phenomenon of photoelectric effect. There was a phenomenon in physics which is called a photoelectric effect. What is photoelectric effect? Photo means light, electric effect means current is produced. So when light falls on certain metals or alloys, right, what happens with a suitable at a suitable frequency, right? What happens? The metal is ejecting out the electrons. The electrons are flowing out of the metal, which is constituting the current, which is called as photoelectric current. So in such phenomenon like photoelectric effect, it was found that the light is not behaving like a wave, but it behaves like a stream of particles, packets of energy, particles. So again they found that the wave theory is not sufficient for explaining this phenomenon. Right. So there was a confusion. This confusion about the true nature of light continued for so many years until there was a new theory called quantum theory of light emerged, in which they said that light is neither a wave nor a particle. The quantum theory means, quanta means a packet, amount. Quanta means it's a certain amount. Quantum theory means they considered that light is traveling in terms of packets of energy, which was suggested by the great scientist Albert Einstein, right? And Max Planck. These two, he started the theory and he did the experiments. Both of them explained the true phenomenon of light. So finally they concluded that light is neither a wave nor a particle. This is called the dual nature of light. Dual in nature. Light is dual in nature. Right? Irumugam adin solluvaanga. You know, people also have got two faces. You would have observed in your daily life. Suppose if your close relatives comes to your house, right? When you are in a vacation, if they come, you'll be happy. Oh, come, let us play, like that you'll say. In case, if you are in a hurried mood that you are going for a movie, at the time if your relatives have come, you say that vanditaya abdinuvanga. So the face will say that welcome, but the heart will say why did you come? So this is what we say dual in nature, isn't it? Everybody has got this, but we cannot reveal everything. No, something will be hidden in nature inside, some only will be showing outside. So this kind of duality is prevailing throughout the universe, like a day and night, hot and cold. It is existing in a pair, isn't it? So in the similar way, light is also dual in nature. Sometimes it behaves like a wave, sometimes it behaves like a particle in nature. That is why we say light is a dual in nature. Now comes the first part of this lesson, reflection of light. Right. This is a reflection of light. Now, if you look at this, a highly polished surface, like here there is a pond or lake. We can consider this lake as a highly polished surface, like a mirror, right? It is reflecting the image of the moon. You can see very clearly. At the midnight, if you look at this, it will be very wonderful to see the reflection of the moon or the stars in the lake or pond or even the river. Of course, only in the still water it is possible to see. And such kind of polished surface or very smooth surface reflects most of the light which is falling on that. Right? When you are talking about reflection, in the lower classes you would have studied about the laws of reflection. Do you remember that? There are laws of reflection. Yes, let us recall that. Right? What is the first one? Here we are going to take a plane mirror, plane surface. Now here, the incident ray, the reflected ray, and the normal, they all lie on the same plane. And the angle of incidence is equal to the angle of reflection. Two laws are there. The first one is the angle of incidence is equal to angle of reflection. Now what is this normal means? It is nothing but, the normal is nothing but, here suppose if we take this as the polished surface, plane mirror for example, highly polished surface. Now the light is falling on that from one direction, like this. Okay? Now how will you measure the angle of incidence? This angle of incidence is not the angle between this ray and this surface, but it is actually measured by using this normal, a line which is drawn perpendicular to the surface. From this perpendicular line, how much this ray is inclined, that is only called the angle of incidence. Similarly, when it is after falling on that, it is getting reflected like this. So the angle between the normal and the reflected ray, this angle is only called the angle of reflection. So the first law says the angle of incidence is equal to the angle of reflection. The second law says the incident ray, the reflected ray, and the normal, they all lie on the same plane. As we have seen now, just now, the incident ray, the reflected ray, the normal, all lie on the same plane. This is the plane. So this is what the second law says. Right? Now these laws of reflection are not only applicable for surfaces like plane surface. Yeah. It is applicable for all types of reflecting surfaces. Not only like a plane surface or a polished surface or a smooth surface or reflecting surface, but also for spherical surfaces. Spherical surface. Whether it is a curved one or, yeah, for all the surfaces, these laws of reflections are applicable. Right. You would have been familiar with this plane mirror because we have been using this plane mirror in our day-to-day life. Every day we are looking at our, at the point of incidence means, see if this is the surface, when you can draw the normal at anywhere, isn't it? You can draw the normal anywhere, but the normal is drawn at the point of incidence. At where it is striking the surface, at the point only the normal is drawn. So at the point of incidence, that is what it says. Okay? Right. Now, since we have been using this plane mirror in our day-to-day life, we have been looking at our same face every day, we are very familiar with the plane mirror. And if you are having a scientific temperament, you would have observed the properties of the image which is formed by the plane mirror, by practice, by approach. Right? So, when you are looking at the mirror, you can understand that the image which is formed on the mirror, plane mirror, is always virtual and erect. These are the 2 points you have to remember. Virtual and erect. What is virtual? Virtual is the one which cannot be caught on the screen. Which cannot be caught on the screen. The image which we see on the mirror, if you just focus this on the surface, any white surface, the same image, our image cannot be seen on the wall. So such kind of image is called virtual. And it is erect. When you look at the mirror, you are able to see the face as it is. It is not upside down or inclined. So it is erect. Right. Now the size of the image is also equal to the size of the object. as you are looking at the mirror, whatever size, whether you are stout or lean, the same image will be seen on the plane mirror. And also it is formed behind the mirror. When you are standing in front of a mirror, we are able to see the image behind the mirror. And at a distance, you know that whatever distance you are keeping, the same distance will be seen behind the mirror. And image is always laterally inverted. Do you know the meaning of this word, lateral inversion? Do you know that? Have you ever heard this word, lateral inversion? No. Here you can see that. In most of the ambulances, the word ambulance is, ambulance is always written upside down. Like, see, for example, I write, say science for example. This is the usual way of writing, right? Suppose if I keep a mirror here, in this mirror, the word will be like this. This is what we say, lateral inversion. That is, or you can say the other way also, you can, this is lateral inversion, but reflection is different from lateral inversion, right? If it is a surface, polished surface means, suppose if I write SEI, the surface will be showing like this. This is called a reflection of the surface. This is reflection, but this is called a inversion, lateral inversion. Like when you are looking at the mirror, or if somebody is looking at the mirror, if you stand behind them and look at them, their right hand will be looking like left hand and left hand will be looking like right hand. Right? That is, if you write L and look at the mirror, the L will be looking like this. This is what we call as lateral inversion. For this reason only, in ambulances you would have seen the word ambulance is written in the lateral inversion. So that, suppose if the ambulance is coming behind us, we are driving a vehicle, car or a bike, right? We do not know whether the ambulance is coming or not. So that when you look at the mirror, this word ambulance will be laterally inverted, so that we will see as it is ambulance. So that we will give way for them. For that reason only, the ambulance word is written in a laterally inverted method. So this is what we call lateral inversion. So whatever image what we see in the plane mirror is nothing but laterally inverted, right? Now using this, we cannot compare the images formed by the reflecting surfaces if it is curved one. It is very difficult, right? So we are going to learn about that, the images formed by the curved surfaces, curved surface, right? That is what we call as spherical mirrors. Spherical mirrors. How will you pronounce this word? Can you tell me? What is this called? How will you pronounce it? Sometimes say spherical, spherical or spherical, sphere or sphere, spherical mirrors. Okay. Okay. When PH comes, how will you pronounce? When PH comes, how will you pronounce? Okay. So this is the task for you. Today, after this class, take your dictionary, and there is a part called in the dictionary, after every word, there is a pronunciation given. Phonetics is given. Phonetics. Phonetics is the way how to pronounce the word, okay? So along with that word, after the spherical word, this word, what is the pronunciation given? Look at the dictionary and tell me in the next class how to pronounce this word, S-P-H-E-R-I-C-A-L. Okay, that is a task for you in English. Okay, learn from that. Let us go to the topic now. Spherical mirrors. Right, now this is another fun what we do every day. Okay, and don't do that now, don't refer the dictionary now, let us just do that afterwards. Okay, now in the dining table we usually if you are using a spoon or a plate, we usually tend to play with this, or even before your mother prepares or serves food, we used to play with the plate, eating plate. We'll just rotate it, reflect it and see the image, and then turn the plate and see the image. Right, it will be frightening to look at our own face in the plate, food plate. It will be in different shapes, right? So just like a fun, it is an activity. You can say, take it as an activity. If you take a large shining spoon, right, like your sambar spoon, where your mother is preparing it, using that spoon, try to view your face in this curved surface of the spoon. Whether it is a smaller image or a larger image. Again, move the spoon slowly away from your face. You can see the change in the size, whether the size is changing or not, whether it is becoming bigger or smaller. Now again, reverse the spoon and just look at the face again. Again, move that towards, away from that and towards you. What kind of changes you are able to see, right? By using this, you can compare the images of the two surfaces. One is on one side where it is curved, the other side is curved outward. In both the cases, we can see what kind of change is there in the image using this curved surfaces that you can try. It will be a fun when you are going for amusement parks. In some places like exhibitions, usually they have this mirror. There will be a big spherical mirror. One will be curved outside and curved inward, what we call as convex and concave. Concave and convex. In that, people used to look at their face. It will be changing that, like a bigger buffoon like or small one, lean one, like that will be changing their face. So that will be funny, very funny to watch. So that one of the activity they usually keep in the amusement parks. Now, you can compare the same spoon, the curved surface of a shining spoon, as a curved mirror, because it is a reflecting surface. If it is reflecting totally with a coating behind, then we can call it as a mirror. So the most commonly used type of curved mirror is the spherical mirror. This is called a spherical mirror, right? Now the reflecting surface of the spherical mirror may be curved inward. This is curved inward, or it can be curved outside. If you turn outside, it can be curved outside. That means the reflecting surface can be coated inside or outside. If it is coated inside, it is a curved inside. If it is outside, curved outside. In both the cases, the reflecting surface can be coated. Now, suppose if we take a ball like, it's a big ball of glass, right? Now in this, I am going to take a section of this. One section here, another section here. Okay? Like a football. The football is made up of glass. Imagine like this. Here, when you take two slices like this, two slices I have taken. In this, if the reflecting surface is curved inward, the reflecting surface, this is the reflecting surface. Okay? If the dark color, if the reflecting surface is curved inward, then it is called a concave mirror. Caved. It is caved, isn't it? So in that way you have to remember. Caved inside. Cave means it's like a curved inside. And similarly, a spherical mirror whose reflecting surface is curved outward, outside, like this. Inside here, the shadow is always called a shining part. That is the reflecting surface. You have to remember, it is the coating. The shadow is always called coating. The other side is called a reflecting surface. So one side is coated inside, here it is coated outside. So if it is reflecting surface is inward, it is concave. If the reflecting surface is outward, it is called a convex mirror. You have to remember, we are talking about mirror. In the later stage, we are going to talk about same kind of objects, things, everything, but it is lens. This is not lens. Lens is a transparent medium. Here we are talking about a one side reflecting medium, other side it is coated with the reflecting surface. So here we have to talk about mirror only. Remember that. Convex and concave mirrors. Two mirrors we are talking about. Okay? Right. Now, we are going to talk about, now we will learn about some important technical words. Right? When it comes to optics, there are so many technical words. Using that only we are going to use that in the formula, everything. So, you have to remember all the technical words and the symbols used for that. Now, let us take the first one. The center point of the reflecting surface of a spherical mirror is called a pole. Right? Now, I said that the lens, it is not lens, it is a mirror. The mirror is taken from a sphere, isn't it? From this sphere only, this mirror is taken, isn't it? So, in this mirror, the center point is called a pole, which is represented by letter P. So, what is pole means, or sometimes multiple choice they may ask. The center point, the center of the reflecting surface of a spherical mirror is called, they may give. So, you have to remember it is pole. And then, I said that the spherical mirror is taken from a sphere, isn't it? So, the reflecting surface of a spherical mirror forms a part of this big sphere, isn't it? And this sphere has a center. This center is called a center of curvature. Center of curvature. That means this is the curve. For this curve, this is the center. Center of curvature. Okay? And it is represented by letter C. Now we have seen two center points. The center point of the reflecting surface is called the pole. The center point of a reflecting surface of a spherical mirror forms a part of the sphere. This, the center of the sphere from which the spherical mirror is formed. That center is called the center of curvature. This difference you have to remember. Okay? And this is represented by letter C. Right. The next one, the radius of the sphere. The big sphere I said, no, from that only we have taken the convex or concave mirror, isn't it? And that sphere has got a radius. So that radius, right? That radius of the sphere of which the reflecting surface is forming a part, and that is called the radius of curvature. We have seen the center of curvature and the radius of curvature. Right? So, what is the definition for that? Radius of curvature, the radius of a sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature, and it is represented by capital R. From here to here, this is called the radius of curvature. Okay, this distance you can see from the center of curvature to the pole. Usually, it is measured from the center of curvature to the pole, and this distance is called the radius of curvature, and this is represented by capital R. Usually radius is represented by capital R. Now imagine a straight line which is passing through the pole and the center of curvature. This is the line, a line passing through the center of curvature and the pole, right? And this is called the principal axis. Principal axis, you have to remember. What is principal axis? It is the imaginary line. It is usually it is not there, but if we imagine an imaginary line passing through the center of curvature and the pole of the mirror, spherical mirror, is called a principal axis. So we have seen first pole, second we have seen the center of curvature, third we have seen radius of curvature, now we have seen what is principal axis. 5 points you have seen. Right? These are the 5 important points you have to learn about that. Now, imagine that we are going to take a spherical mirror, right? Here, though it is like a single spherical mirror, it is actually has got so many mirrors kept inside, right? So that it becomes a very big spherical mirror, right? Now, what is that we are going to see from here now? I am going to keep this towards the sun, okay? We can call it as a furnace, which is useful for heat the objects. Solar furnace we can say, right? But now imagine that it is a spherical mirror, concave. You can see that concave mirror. It is curved inward. Totally it is reflecting surface. Now what is it going to do? Look at that. Now this is the mirror here, right? It is focused towards the sunlight, and at one point I am keeping the wood. See what happens to the wood? The wood is starting burning. You can see how the flame is created. Fumes are coming out of the wood. No fire is there, no stove is there, but it only kept near the curved mirror, actually big curved mirror, which is focusing towards the sunlight. Now you can see how it is catching fire easily. It is burning, you can see. Instead I am keeping a paint can, like a Coca-Cola tin, like that tin can is kept. You can see how it is making a drill, like gas welding. You can see it is making a hole. Now you can understand how much powerful the light will be. The focusing light, you can see that now how it is catching fire. Now the tin can is kept here. Now you can see it is making like, it is melting. Almost it is cut into two pieces. That much heat is created when this concave mirror is kept focused towards the sunlight. It becomes, see, it has become two parts. Now the next one is, I am taking a piece of mud. You can see. Yeah, see that how it is burning. Even though it is a piece of mud, the mud itself becomes red hot. So why is it? Because the light from the sun is converged at a point where we are keeping the object. That is the point where the light is converged as a sharp bright spot by the mirror. So in fact this spot of light is the image of the sun actually. The image of the sun is falling on the curved mirror, and it is got in place of screen only. I am keeping the object here, right? So at that point where we are getting the complete image or heat, we call it as the focus of the concave mirror, right? This heat which is produced due to the so many rays which is falling from the sun on the curved mirror is almost converged or concentrated, and so that it becomes more powerful, and it is making the paper burn or ignites the paper. Now we can see the distance of this image from the position of this mirror is only what we call as the focal length. What we call it as focal length of the mirror. Focal length of the what? You cannot imagine. See, even you can see that the iron or the tin, everything is burnt out. If you keep your hand will have a hole, or your hand will catch fire because it has got fat, it is like a petrol, it will catch fire. That much very hot it is, right? Not only with this, it is only not only with this big furnace. Even you can take a small lens and take, or ordinary mirror, small mirror also you can take and just focus it. But with plain mirror you cannot do that. Plain mirror will always reflect back, but only the curved mirror will converge the rays. That is why I said from the center of this mirror to the point where we are getting the heat, this distance is approximately is giving out the focal length of the mirror. Focal length of the mirror. Okay. So this is what an activity which will help us to understand. Now, what do you understand from this? Look at that. When you are focusing that towards the sun, a number of rays parallel to the principal axis of this mirror, concave mirror, right? a number of rays parallel to the principal axis, they are falling on the concave mirror. That is, it is infinity. The sun is here. From the sun, there are so many rays. Right? The light is traveling and it is falling on the concave mirror, which is parallel to the principal axis. This is the principal axis, which is parallel to the principal axis. It is falling. Right? Now, observe the reflected rays. They are all meeting at one point, and that point will be lying on the principal axis. You can see that how they are all focusing. Now, see that they are all falling parallel to the principal axis. After falling on the mirror, they are all converging at one point. You can see how they are converging. Have you understood? And this point is called the principal focus of the concave mirror. From this we can get the definition of principal focus. Principally it is focusing. How it is focusing? What is principal focus? A number of rays falling on the concave mirror parallel to the principal axis. After reflection, they all meet at one point on the principal axis of the mirror. That point is called the principal focus of the mirror, which is indicated by letter capital F. Right? Do you understand? This axis, you know, the principal axis is falling, going through the center of curvature and the pole of the mirror. That is the principal axis. All the rays are parallel. Right? Now you may think that, sir, you have taken only 4-5 lines. Do you think that light is having only 5 lines? But it is only imaginary line. Light is like a bundle of rays, bunch of rays. Like a torchlight, if you shine, we call that light which is coming out of torch is a beam. Beam of light, we say. A beam of light has got a infinite number of rays. But for practical understanding of the nature of light, we just indicate that by only few lines, so that it is easy for us to locate the image. Right? Now, the point where all the rays after reflecting is meeting is called the principal focus, which is called a capital F, indicated by letter capital F. Now, the next point you have to remember. Similarly, if it is a concave, we have already seen the concave. Now, if it is a convex lens, right, curved outward this way, right, this way. Okay, the plate is kept upside down that way, right? So what will happen in this case? How to locate the principal focus? The reflected ray, they may appear to come from a point on the principal axis. This point is called the principal focus. That is, they may appear to come from this point, because you know that if the mirror is that this way, after falling the light will be reflected in different direction. They cannot converge because the surface is curved outward. So when the light falls on that, it will be thrown out in different directions. Isn't it? But in which direction it is going? When you extend this line behind the mirror, all the lines would have started from one point, and that point is called the principal focus. So remember that if it is concave mirror, the principal focus will be in front of the concave mirror. If it is convex mirror, the principal focus will be always behind the mirror. This is convex mirror. So the principal focus is behind the mirror. All the rays after reflection, they appear to come from a point. They appear to come from. So that point which is behind the mirror is called a principal focus. That is also indicated by capital F. Remember, I am saying capital F. That means we are going to use small f for some other reason. Okay? Yeah. Now, the distance between the pole and the principal focus of the mirror. Just now we have seen using the furnace, solar furnace. Right? The distance between the pole and the principal focus of the mirror is called a focal length. So this is focal length. The distance between the pole and the principal focus is called a focal length. That means when you are keeping a mirror, concave mirror, in front of an image, right? You keep the mirror like this, right? Focus that towards a distance tree, and the tree image will fall on the mirror. And if you keep a white screen on that, so that slowly adjust that, you will get the image at one point. The image of the tree can be caught, and that image is the point where we are getting the principal focus. Okay, and the distance between the principal focus and the pole, that is the midpoint of this mirror, this distance is called the focal length of the mirror, this mirror. So this is how we have to measure the focal length. Here we are using small f. The small f indicates the focal length, capital F indicates the principal focus. This difference you should remember. Now the next one, the diameter of the reflecting surface. Suppose if we take any spherical mirror, it has got a diameter because it is taken out of a big sphere, isn't it? So the diameter of the spherical surface of a spherical mirror is called aperture. Okay, you can see the diagram here. In this diagram, the distance Mn, this distance Mn is nothing but the aperture of this mirror, concave mirror. But here in this lesson, whatever the mirror we are talking about, all these mirrors will have a small aperture. That is, the aperture is much smaller than the radius of curvature. When you talk about the radius of curvature, this is the radius of curvature. From the center of curvature to the pole, this distance. Okay, what do you understand from that? Suppose if you take a sphere, the spherical mirror can be taken by making a slice over this, isn't it? Now compare this distance now. This is the, for example, this is the center of curvature and the pole, and this is the radius of curvature. Right? Now if I take this kind of a mirror, spherical mirror, this distance is same as the distance. Both are same. Am I right? But I am going to take as much smaller lens like this. Now see the aperture now, this is the aperture. See the distance from here, it is much more. Okay, such kind of lens only we are going to discuss in this class. So, the spherical mirror whose aperture is much smaller when compared to the radius of curvature. Such kind of mirrors only we are going to take for discussion. Okay, now for spherical mirrors of small aperture, as we have discussed now, it is found that the radius of curvature is equal to twice the focal length. What will happen? We will not be able to get the image. You know, for making the practicals in the lab, if you are getting a big mirror, right? In one lab, if you keep the mirror and make the focus, you will have to take the screen to the next building and get this image. So that you will have to take, for lease of the next building, so that you will complete the practical. It's very difficult for us to do, isn't it? That is why we take very small spherical mirror, so that we can complete the experiments in the lab itself. It's only practical application. Okay. Okay. Now, here we found that the radius of curvature is twice the focal length. Twice the focal length. This formula you have to remember. For spherical mirrors whose aperture is small, for small aperture, the radius of curvature is equal to twice the focal length. Do you remember that? What is that? Here if you take the spherical sphere, for example, right, we have taken a, say this is the spherical mirror. Okay, right? Now if I put a point here, and this is the radius of curvature, right? Now if they say R is equal to 2F, what do you mean by that? That means the lens after reflection, it will have the principal focus here, that is capital F will be here, so that this distance is F and actually this distance is also F, so that both will be equal. So the principal focus of this spherical mirror whose aperture is small will be in between the radius of curvature, exactly in the middle of the radius of curvature. Okay, lies midway between the pole and the center of curvature. Pole and the center of curvature. This is the pole and this is the center of curvature. So for spherical mirrors whose aperture is small, the principal focus will be midway between the pole and the center of curvature, or it will be twice, the focal length will be twice. That is, radius of curvature will be twice the focal length. So you can compare that. Which will be greater in this? Radius of curvature will be greater. For small aperture spherical mirrors, the radius of curvature will be bigger and focal length will be half of that. The other way also we can put. From this we can say f is equal to r by 2. This also you have to remember. Other way, converse of this. So sometimes they may be asking you for spherical mirror whose aperture is very small. If they give you the radius of curvature, you are asked to find out focal length. That means simply you have to divide by 2. R by 2 will give you the focal length. Okay? So this is the one of the inference you made from this. Now, using this, we will learn what are the different ways that images are formed by using the spherical mirrors. Now, already we have discussed about the image formed by a plane mirror. We also know, because we have been watching the plane mirror every day to see our face, and everywhere in bikes, car, everywhere in hotels or in the barber shop, everywhere you are able to see that. We know the position, relative size of image formed by them. And also, when you compare with that, how about this image formed by spherical mirrors? How can you locate the image formed by a concave mirror for a different position, whether they are real or virtual, whether they are enlarged, whether they are diminished, very small, or whether they are of the same size? To understand all those things, it's only possible when you do a small activity in your lab, and then only you can understand that. Because by simply explaining this, it is very difficult for you to understand. If you take a spherical mirror, small aperture spherical mirror, and do the activity in your lab, it will be very easy for you to understand. Otherwise, simply we say theoretically, keep it at principal focus, keep it at center of curvature, keep it at twice the center of curvature, keep it at infinity. If we say simply, it will be confusing. But instead, after you learn this, just try to, even you can buy that. After all, it costs some 5 rupees or 10 rupees. You can get it from the shops which is available. Probably it may be available in your Coimbatore. You can ask your dad to purchase, okay, spherical mirrors, okay, and using a candle, you can perform the activity in your house itself. This kind of small experiments you have to do at home and enjoy. You need not spend more time in the lab. You can spend more time at house so that you can learn some from that, right? Try to get one. Different spherical mirrors are available. Now, the nature, position and size of the image formed by a concave mirror is depending upon the position of the object at different points, which is relative to P, F and C. That is, we are keeping the object with reference to pole. At what distance from the pole you are keeping, or at what distance from the principal focus you are keeping, or from what distance from the center of curvature. Depending on all these points, the size, nature or position of the image will be differing. Okay, and sometimes the image may be real, or sometimes for certain positions the image will be virtual. Sometimes, depending upon the position of the object, it may be magnified or diminished, or we call it as reduced, or sometimes may be same as the object, okay, for different position of the objects. So at what position if you keep the object, where will you get the image, and how to get the image, what kind of image, what is the nature of the image, all those things we will just see in the next class by keeping the object in different positions, and also learn to draw the diagram. We call it as ray diagram to represent the image formed by a concave mirror at a different position of the objects. Okay, that we will learn in the next class. And in the meantime, if possible, okay, try to get the mirror. Usually these kind of small items like magnetic compass, bar magnet, or spherical mirror or lens, everything can be got from the suppliers. You can ask your physics teacher or the computer lab assistant in your school, and you can get the address of the suppliers. Okay, you can call the suppliers and you can just ask them to send it to your home address. Very simple objects, very, very small items can be bought at the cost of just 100 rupees, 500 rupees, all those things. So that you can learn a lot, because it is very difficult for a teacher to spend time individually in the lab. In a group he may be teaching, and sometimes you may be curious to know about a particular property of the lens, where the teacher may be very fast in teaching the other concepts, and you will be struck with one concept and you will be just imagining and trying to explore. So at that time you will be losing, or you will be losing the concentration of the on the other points. So for such reason only I am asking you to buy certain items like this and start doing the experiment. Build your own lab in your house. That will be giving a lot of benefits in the future studies. As you go to the higher classes, you will become a scientist, right? So that when it comes for an exhibition or any talent display, at the time you become a magician. All will be wondering, already know all those things. Like this will be very interesting. So try to do that. Remaining we will continue in the next class. Okay, thank you.